Welcome to lecture 10. Before we start with the alpha substitution reactions of aldehydes and ketones, we will shortly revise the last lecture. Last lecture, we focused on nucleophilic addition reactions of aldehydes and ketones with oxygen, sulfur, and nitrogen nucleophiles. And we learned that the addition of water yields hydrates. Moreover, we learned that the addition of alcohols yields acetals. And similar to the addition of alcohols, the addition of thiols yields thioacetals. Finally, we had a look on nitrogen nucleophiles, and we learned that the addition of a primary amine yields an imine, whereas the addition of a secondary amine yields an enamine. Moreover, we had a look on the addition of hydroxylamine, which forms an oxime, and the addition of hydrazine yields hydrazone. And today we will focus on the alpha substitution reactions of aldehydes and ketones. Alpha substitution reactions involve the replacement of a hydrogen by another group at the carbon atom on the alpha position, so hence on the carbon next to the carbonyl group. If we now have a look on the aldehyde or ketone, we can see here the carbon atom, which is part of the carbonyl group, and then the neighboring carbon atom has a hydrogen atom, and this is the alpha position. And the mechanism involves an intermediate enol or enolate ion, and both enols and enolate ions are nucleophiles, which can then react with an electrophile to introduce a new group at the alpha position. The enol looks like this, so we have a carbon-carbon double bond, and attached to this carbon-carbon double bond we have an hydroxide group. And the enolate ion looks like this. You can see that we have now a negative charge in the molecule, and the enolate ion is stabilized by resonance. So you can see here is the negative charge on the carbon atom, but of course we can have a resonance structure where the negative charge is on the oxygen atom. And then the final product is our aldehyde or ketone, which has, instead of a hydrogen atom in alpha position, now a new group in alpha position. Aldehydes and ketones with hydrogen atoms in alpha position are in equilibrium with structural isomers, the so-called enols. And for most aldehydes and ketones, the most stable structural isomer has a carbon-oxygen double bond and is called the keto form. The enol form is derived from the keto form by the transfer of a hydrogen atom, and it has a carbon-carbon double bond with a hydroxide substituent. The interconversion of the keto into the enol form is called Keto-enol tautomerism. And at room temperature and neutral pH value, this interconversion is relatively slow. So to increase the rate of the keto-enol tautomerism, either an acid or base catalyst can be used. And as example, we have here the keto-enol tautomerism of propanone. You can see the keto form of propanone here. And the enol form of propanone is depicted on the right side. We have the carbon-carbon double bond, and attached to it the hydroxide group. As just mentioned, most of the time this equilibrium lies on the side of the keto form. So this is indicated here. We have more than 99.9% of propanone and only less than 0.1% of the enol form. In the acid-catalyzed tautomerism, keto form gets in a first step protonated on the oxygen atom of the carbonyl group. And then in the subsequent step, this positively charged intermediate gets deprotonated, and hereby the enol form is formed and our acid catalyst is regenerated. As you can see here, for this deprotonation water is used, so water acts as base. Conversely, in the base-catalyzed tautomerism, a base such as hydroxide deprotonates the keto form in the first step. Hereby an enolate ion is formed, and this enolate ion is stabilized by delocalization of the negative charge onto the electronegative oxygen atom. And in the final step, the oxygen atom gets protonated and the enol form is generated while the hydroxide ion is regenerated.